Okay, sound doesn't work. I'll just use my laptop. Okay. So before we begin, do you have any questions at all? No? Okay, so most of the course we covered finite difference methods, right? And then we looked at some other approaches. For instance, we've looked at vortex methods. And today I want to show you how Fourier transforms can be used to solve differential equations. Again, there are advantages and there are disadvantages. So you've all probably encountered Fourier transforms before, right? But have you thought about what it means? What's the physical meaning? So we just have, let's see, the formula. Okay, so we say if we are given a sufficiently smooth function, let's say f of x, okay. The Fourier transform for that it's so we can say f hat of kappa equal integral minus infinity to infinity f of x e to the minus I f of x dx. Okay, so this is a very, very, very famous formula. But what does it mean? I mean, what are we doing here? We have an f of x and we compute some integral. We get an f hat of kappa. What is this kappa? So this kappa is called wave number. If we are talking about we work in space. Or mathematics doesn't care if you work in space or in time. So this will become frequency. If RHS has, at the right hand side has time t instead of x. Okay, so you have seen this before, but what does it mean? What do these wave numbers and frequencies mean? Let's talk about that first before we come to what exactly f hat means. Okay. So what does wave number mean? Do you know what frequency means?
1 over time.
Frequency is 1 over time, right? And physically it represents something. It represents, what does it represent?
Like how often something happens?
Yeah, the unit for frequency is hertz, like 1 over second. And if we hear a sound at, let's say, 20 hertz, that just means we are hearing 20 vibrations in 1 second. We hear one at 2000 hertz, 2000 vibrations in 1 second. But what is the sound? It's basically a signal, some signal, right? So we'll play with some FFT demonstrations in MATLAB. But you're right in saying that frequency is just how often something happens, right? So if we have, let's say this is time for 1 second and 0 seconds. And if I plot a particular signal, 1, 2, 3, 4, okay? Frequency is
4 hertz?
Yeah, frequency is 4 hertz. Nu or F Okay, let's just use f. It's 4 hertz. Okay. What is the time period?
Quarter second.
Yeah, it's 1 over f, 0.25 seconds. Okay, and here, we just see, okay, yeah, this is the time period. So this is one full wave, this is the second full wave. In space, nothing changes. T becomes x, capital T becomes lambda, wavelength, and frequency becomes wave number. The equivalent variables in space one, two, three, four. Okay, this is one wavelength, second wavelength, third and fourth. Okay, let's see wavelength. Lambda is what?
Uh, 0.25.
0.25 what?
No units for.
Yeah, I didn't give you anything, right? So let me say this is L. So lambda is L over 4. We can say this is 1 meters. Okay. So lambda just represents 0.25 meters per full wave. Okay. And kappa is the wave number. This is 1 over lambda, which is 4 in this case. And this just says we have 4 waves in 1 meter. Make sense? So it's completely equivalent. There's no difference in space or in time. All right. Which is in a simulation, if we were to represent this on a grid, what would be more difficult? Representing low wave numbers or high wave numbers?
High wave,
Why high wave numbers?
because there will be many waves in just a meter, so we have to define the grid more.
Yeah, does that make sense? Does anybody disagree or agree? Makes sense, right? So if we have kappa equal 4 here, we have 4 waves in 1 meter. If kappa equal 40, we would have 40 waves in 1 meter. So if kappa equal 40, it would look something very, very convoluted. Okay? And this means that to represent this function accurately on a grid, discretized grid, you will need a lot more points. Okay? This was not the case with a low wave number scenario. You could just use a few of them and you would be able to recreate the signal pretty well. Okay? But if I use this delta x spacing in this scenario, I might just go from 1 0 to the next 0 to the next 0. So I might end up saying, this is a flat line. Because, when we're doing these computations, we don't know what the function looks like. We just have the grid points and the y values at these grid points. Okay? So this you might have heard of. It's called Nyquist frequency. Nyquist criterion, Nyquist frequency. Do you know what this is? Have you heard of this before? Yeah, okay. So it just says that the number of points I use should be at least 2 times the wave numbers I want to capture. All right, if we're talking about about time, the sampling frequency should be 2 times the signal frequency. That's what it says. And this is the reason. If we don't, the signal we try to reconstruct might be some random signal. It might end up being some random signal. Okay, so yeah, whenever you see wave number kappa, just think of it as the equivalent of frequency, but in space. There's nothing special about it. All right, so let's go back to our Fourier transform. Yeah, so let's talk about theoretically what it means first, then we will do some examples on the computer. So let's say we have f at kappa equal minus infinity to infinity f of x e to the minus I kx. Okay, so at this point we understand that x is in real space and kappa is wave number, real space. It's the real space variable. This is our given function. And f hat is called what?
Fourier transform.
The transform is the operation, right? It's the integral we compute. But when we get the number out, do you know what it's called?
The mode, the Fourier mode?
Yeah, it's called the Fourier mode, Fourier coefficient, right? So this is the Fourier coefficient. Or the Fourier mode. Well, not the Fourier mode. Fourier mode would be the corresponding sinusoid in kappa. So Fourier coefficient. Fine. There is this formula. What does this mean? What does this Fourier coefficient represent? Physically, can we assign some physical meaning to this? Or is it just mathematical and you don't care?
It's the weight for the wave number which is present, which might be present in the setting we are looking at.
Okay, so you're saying it's the weight for the wave number that might be present. Okay, yeah, okay. Can you go a little further? What are we trying to do when we compute these Fourier coefficients? We're given a random, or not random, a nice smooth f of x. What are we trying to do?
We are trying to decompose it into like the frequency space or the wave number space, and then we are looking at different components and how much weight each component is having. This will be determined by the Fourier coefficient.
Yeah, so the reason we are interested in computing Fourier coefficient in the first place is we want to break up our signal f of x into individual sines and cosines. Okay? So that was why this technique was so revolutionary. You could take any signal you want and you break it up into small, very simple signals, sines and cosines. Okay? And these sines and cosines can have infinite frequencies, going from kappa equals 0 to kappa equals 10 to 100,000 to whatever, right? So that's the basic idea behind Fourier modes or this Fourier transform. If we have a sufficiently smooth function f of x, we can decompose or break it up into decompose it into a linear combination of sines and cosines. Okay, so if we look at a cartoon example, if we have a signal that looks like this, okay, again, this is just a schematic representation. Okay. This, we can say, okay, this, if we have x equal, let's say x goes from 0 to L, this is actually a linear sum of these individual sines and cosines. So one sine wave with frequency 2, another with a much higher frequency, okay, but a different amplitude. Okay, here the amplitude might go from 0 to 5, here the amplitude might go from 0 to 2, let's say. Again, this is just a cartoon example. So it's the Fourier coefficient is just trying to decompose this original signal into a linear combination of sines and cosines. That's it. Okay, and each of these sines and cosines have a multiple in front. Okay, for instance, here if the amplitude goes from 0 to 5, the multiple in front is 5. It's sort of the strength of this particular mode, so this Fourier mode. And that's exactly what this f hat of kappa represents. Okay? This f hat of kappa will give us 5 or 2 in this case. Okay? So in an abstract sense, all of this seems nice, but it actually works if we try to look at this numerically. Okay, so let's do some examples. And before I do that, let me just tell you FFT is fast Fourier transform. Okay, so analytically you would evaluate this whole integral, but what's the problem with doing this numerically? Can I compute the integral? When you integrate, let's say, x squared dx, the answer is x cubed over 3 plus c. Okay, but we don't do that when we do numerical computations. We don't do a simple integration. So somebody was saying something. Go ahead. What were you saying? Do you know what I mean? So we have this continuous integral.
Yeah, so it will be, when we have a finite domain, we cannot compute this integral because of the limits. It is minus infinity to infinity.
Yeah, that's one problem, yes.
And we a priori don't know the function f of x.
Yeah. You're right. In both cases, that's the main two problems. So it's minus infinity to plus infinity. Some functions can have a nice integral from in those limits, but when we do computations, we have to truncate somewhere. We have to limit our domain. Also, f of x, we don't have the analytical f of x. We just have samples, right? We're just given x, y values. So the fast Fourier transform just treats the integral as a summation. Kappa goes from minus infinity to infinity, f of x e minus I kx delta x. Okay, and if we have a total of n grid points, what is the maximum kappa we can have?
N by 2.
Why n by 2?
The Nyquist frequency?
Nyquist frequency, right? We just said that we need to have at least twice as many points as the frequency we're trying to represent. So if we have n grid points, the best frequency we can represent is n over 2. Okay? So we can further truncate this kappa equal minus n over 2 to n over 2 f of x e minus r k x dx. Okay, this might still seem a little mysterious, so let's look at what we would do with a simple sine wave. So, I'm just given these data points. Let's say, so this is y and this is x. Okay, I'm just given these data points and I'm said, what is f of x here? What does it look like? Looks like a sine wave, a very simple sine wave. And we can actually compute f hat of kappa using just these points here. So what would you do? You would take, so this is x1, this is f of x1, this is x2, this is x3, this is f of x2. Okay, so we can basically plug these x and f of x's in this summation. So you would have, why did I write kappa? This is not right. Kx, x. So this goes from x equal minus infinity. I've written the inverse transform. Let's see. It should be I equals 0 to. The thing I wrote would be valid for an inverse transform, not for a forward transform. So let's say this is I k I, and this is delta x I, f of x I. Okay. So we have the formula, we just plug stuff in. So we have f of x1 e to the minus I kappa x1 delta x. Let's assume delta x is constant, plus f of x2 e to the minus I k x2 delta x plus blah blah blah, right? So we basically sum up all these. And well, we still cannot sum up all these because we have an available that's unknown to us, kappa. Okay? So does this make sense or is it confusing? Makes sense? Okay. So we know f of x1 given to us numerically. We know delta x. The whole thing is divided into delta x's. We know x1 because we are looking at different points. What is kappa? Where should I get kappa from? Think of what we're trying to do. We are trying to break up fx into frequencies. Okay? Frequency kappa equal 1, kappa equal 2, kappa equal 3. And with this equation, we are basically trying to figure out how strong is each of these frequencies. So
it will be multiples of the grid delta x.
Okay.
Like the inverse of 1 over n times delta x would give me, or n over delta x would give me the wave number kappa.
N over delta x is just one number. N is a constant, delta x is a constant.
N would vary from
multiples. Yeah. Okay. Yeah. So you're right. Yes. To keep things simple, what we can say is kappa equals 0 represents what?
Infinite length.
It represents the mean, the average. Okay. Okay. If I say something that doesn't make sense, stop me, because these are very simple things, but they take a little while to get used to. Okay. So we plug in different values for kappa. Values for kappa ranging from, let's say, minus n over 2 to all the way to 0 to 1 to n over 2. Okay, so, I have a nice formula here, but kappa is unknown. I will plug in kappa equals 0. That gives me f hat of 4, kappa equals 0. I will plug in kappa equal 1. That will give me f hat of kappa equal 1. Okay? To get the corresponding f hat of kappa. So let's say this is 0, this is 2 pi. What is f of x? The orange f of x? Given f of x seems to be just looking.
Sine of x.
Yeah, it's sine of x. So it's sine of x. All right. So, which implies we should recover for kappa equals 0. What is f hat of kappa?
No, you're not on the screen anymore.
I'm sorry.
You're not
Oh,
on the
sorry.
screen anymore.
All right. For kappa equals 0, what is f hat?
Should be 0
Why should it be 0?
because
It's 0.
Sine 0 is 0. Okay. So, yeah. Go on.
yeah, because there is no frequency component corresponding to this sin x.
Yeah. So, see, that's where it gets a little tricky to get used to. F of x and f hat of kappa are not the same, right? So f of 0 would be 0, yeah. But f hat of 0 means what is the strength of the sinusoid with wave number 0? Wave number 0 just means a flat line. So if I break this up, this whole signal up into a flat line and sine of x, sine of 2x, sine of 3x, what is the strength of that? So for the flat line, we see this is centered about 0, right? Y equals 0. So f hat of 0 will be 0. If we had a function where the center line was not at 0, if we were given this thing, if we were given that, let's say, this is the 0 axis somewhere over here. This is the x-axis, this is the y-axis, this is y equal 5. So this is basically saying my f of x is, what is f of x?
5 plus sine x.
It's, what's more?
5 plus sine x.
It's 5 plus sine x, right? So, in this case, f hat of 0 would be
5.
5. Yeah. So yeah, that's exactly what it means. Kappa equals 0 represents the mean value, the mean constant value, right? Constant. So if we have 5 plus sine x, the 5 is the constant. Fine. So this is just a side note. Kappa equals 0, which means f hat of 0 would be equal to 5. Okay. All right, let's go back to our original example. Kappa equals 0 gives me 0, right? Fine. For kappa equal 1, what will I have? F hat of 1, I will get for this original orange function. Does the question make sense? No, it doesn't. Okay, so what did we say this f hat represents? It represents the strength of each frequency. We said the strength of frequency number 0 is 0, okay, or fx equals sine of x. F hat of 1 means what is the strength of kappa equal 1? So if I write this as, in general, if I write this as sine of kappa x, can you tell me now? For our functions, f of x equals sine of x, f hat of 1 will be, okay, it will be 1. Okay. Why? Because this is saying, what is the constant multiplying my sine of x? Constant is 1. If this were 10, this would return me 10. If this were 0.9, this would be 0.9. Does this make sense? Okay, what is f hat of 2? Or f of x equals sine of x.
One of those would be zeros.
This will be 0. What did you say? One of
Yes,
those?
all
The remaining will be 0. F hat of 3 equals 0, f hat of 4 equals 0, f hat of infinity equals 0. The reason for that is my original signal only contains one pure sinusoid with frequency 1x. That's why only f hat of 1 is equal to. Okay, everything else is 0. So let's, just to make it super clear, let's take another example. Okay, let's take g of x equal, what do you want me to take? 0.9 plus 7.5 sine x plus 3 minus 3.2 sine 3x. Okay, let's break this up very quickly. Let's say f hat of 0 is
0.9,
0.9, yes. F hat of 1 is
7.5,
7.5. F hat of 2 is
0,
0. F hat of 3 is
3.2.
minus 3.2. Make sense now? So that's basically what the Fourier transform does. And you know, in reality, no, not f hat, sorry, g hat. So these are all, this was the function g hat. So this is g hat. In reality, no function that we deal with will look like a nice sum of sines and cosines. And the Fourier transform is trying to make it that way, right? It's just trying to give you, okay, if my g of x were to be broken up into sines and cosines, these are the things you would multiply in front of all of these sine signals and sine 2x and sine 3x. That's it. That's what the Fourier transform does. It's very, very powerful and very, very useful. One of the most useful things, algorithms in mathematics. Okay, do you believe that? Does that really happen? Just because Joseph Fourier said that this is true, should we believe him? Let's try to do some examples, okay, and then let's see if that is indeed true. Okay, so we're talking about signals, right? So let's generate a signal. Let's say x goes from 0 to 2 pi and let's say 1,000 increments. Can you see what I'm typing? Is it big enough? Yeah. Okay, let's say y equal sine of x. Okay, and let's plot this. Now, okay, so it's a sine wave going from 0 to pi. Fine. Let's take the FFT of y, and this will be called y hat. This is too many numbers. I'm going to reduce this to 11. What should y hat look like? The vector. It will be 11 long. What should it look like? We're taking a pure sinusoidal signal.
It will have a non-zero value at one place and zero value at other place.
Yeah, so y hat will be a vector containing y hat of 0, y hat of 1, y hat of 2, blah, blah, blah. And blah, blah, blah goes up to n over 2. So in this case, 5. Okay, I will tell you why 5. And it will contain all the coefficients going from 0 to 5 and then minus 1 to minus 5. Okay? And each program you use will arrange this differently. The way MATLAB arranges it is, let's say, kappa vector goes from 0 to n over 2, and then from minus n over 2, 2, n over 2, minus n over 2 to minus 1 to minus 1. Will this work?
We haven't defined n.
N, yes. So let's say n equal length of y. Will this work now? Will you get only one non-zero value for y hat?
No, now we will be getting 2
You will get two values. Why?
on the negative side as well, for the negative wavelength.
Yeah, you will get non-zero value for kappa equal 1 and for kappa equal minus 1. Okay? This is complex conjugates. Fourier transform is symmetric in imaginary space. If you're doing real transform of a real signal. Yes, but there's still one thing missing. I have not deleted the last value. So remember, the first value and the last value are exactly the same. When we did periodic copy, we have to be careful of this, not to take the right neighbor of the last value to be the first one, goes to the next one. So yeah, to make sure Fourier transform doesn't trip up there, you will just remove the last value. Okay. All right, let's see. This should work now. Let's cross our fingers and hope it does. Okay, seems to work. So this is my original y and x, and let's see y hat. First term is 0, second term is non-zero, third term 0, 0, 0, 0, 0, 0, 0, and the last term is 0. So if we look at the corresponding kappa, look at the corresponding kappa, why did it not? Oh, yeah, the reason why it should be a plus. Okay, so let's look at y hat again. Y hat is that, and kappa vector is that. Okay, perfect. So kappa equals 0, f hat should be 0. That's true. Kappa equal 1, f hat should be some value. It's a minus 5i. Okay? And we will see why it's minus 5i. It makes sense. Okay? And we try to expand it on paper. F hat of 2, 3, 4, 5 are all 0. 0, 0, 0, 0. Okay? And f hat of minus 1 is this. Okay? Fine, they're non-zero. But we said we have a pure sine x here. And f hat should be equal to 1. Okay? So again, every software has its own implementation. So here we just need to divide by n over 2. N over 2 or n? No, divide by n. Yeah, divide by n. To get the actual value. Let's see. Wait, what did I do? What did I do? If we don't do this, every time we change n, we will get a different yn. Let's do that and let's see what happens. So let's see. For 11, we will get, this is 5, okay? If we change this to 21, that will become 10. Yeah, see, now it becomes 10. That's because it has to be normalized. So we just normalize this correctly, and now it will always be 1, but 0.5 over here and 0.5 over here. Let's see, we go back to 11, and we will get again 0.5. Yeah, 0.5 and 0. No, physically the Fourier coefficient should not depend on, the value should not depend on how many points you're using. So it has to be normalized correctly.
So why did you take that xn equals to empty vector?
Okay, so if I don't do that, so right now you are happy with the result. Only one Fourier coefficient is, only one wave number gives you non-zero Fourier coefficient, either +1 or -1. If I don't do this, see, there's all these imaginary numbers now. There's an imaginary non-zero number all over the place. And this happens because now the very first point, come on, but it is not working in MATLAB. Why? Okay, fine, I will zoom in. See, this point 0, 2 pi, 2 pi, 0 is exactly equal to the very first point.
Yes.
0, 0. So when FFT does assumes periodicity, oh, I forgot to tell you about periodicity. I will tell you. So when it assumes periodicity, it just takes the function and repeats it. Okay. And if you have 0 and 0 here, you take a complete exact copy, put it over there. What happens? You have a mismatch here. It's not a nice, continuous, smooth function. You have a 0 and a 0 repeated. So you have to remove that. Okay? And then it's perfect. You have a 0 here, something less than 0, and then the incoming value is exactly 0. Does this make sense?
Yeah.
Yeah? Okay. It's the same exact thing that happened to us when we were taking periodic boundary conditions. We had to take care not to say the last element is the neighbor of the first element, the last two, the next to last is the neighbor of the first. Okay. It's that, for that reason. And internally, FFTW is built such that it assumes that you're getting rid of the very last. Okay, so yeah, we need that.
Is that same for in all the other frameworks?
Anything that uses FFTW, yes. So FFTW is a library. It's called the fastest Fourier transform in the West. That's the name. And I think it was coded at MIT, I forget, in the 90s. And it's the fastest implementation of doing this, the summation that you were talking about. Let's switch to the camera for a second. See, this summation is expensive because you have to go all the way from x equals 0 to L, and you have to keep doing this for kappa equal all the values that you need. So from -n/2 to +n/2. So this is a convolution and it's expensive. But Huli and Tukey found out a very ingenious way of doing this very, very fast. That was implemented in a library called FFTW. And even today, almost everybody uses it. There's nothing that's faster. Okay? So yeah, FFTW assumes it. And even in FFTW, there's different functions you can call it. They assume different things. So you always have to be careful. What is the function assuming? And I give it the correct data. Does all of this make sense?
And FFTW is it some parallel implementation of this or the Cooley-Tukey thing?
FFTW is the Cooley-Tukey implementation.
Okay.
I don't think you cannot do this in this is not a fine-grained problem. You cannot say I will do an FFT separately. You need data from all x locations. See, this summation needs all x values and all fx values. So yeah, fine, even if you're computing this individually, one computer is computing this half, the other is computing this half. They will have to communicate at some point. So you can never decompose data perfectly. Okay, so I said I forgot to tell you about periodicity. This infinite integral, minus infinity to infinity, if fx is periodic, then you can just evaluate this over the periodic domain, x equal minus pi to plus pi, or x equals 0 to 2 pi, okay, or x equal minus 3 pi over 2 to 2 pi over 2. So as long as your fx is periodic within a certain domain, you can truncate this without any loss in accuracy. Okay, that's not always true. Real world signals are not this nicely periodic. So we have to do some sort of windowing, saying, okay, I will assume my function is periodic in this large window. I know that I'm making some error, but what can I do? I have to do something. Especially with time signals, when the time signals are coming in, you have to, have a large enough window and then say, okay, I will do my FFT in this window. What was the question you asked?
About like what FFT is exactly, why we call it fast Fourier transform.
Yeah, so it's basically computing this summation in a very clever way. It's decomposing it into halves, and that into half, and that into half. I went through the algorithm once. It's a very elegant algorithm, but I don't remember everything right now. But yeah, Cooley and Tukey were the ones who came up with the idea. Okay, so yeah, we're talking about periodicity. Yeah, so the signal needs to be periodic for us to evaluate data. Okay, let's go back to the computer. Okay, so fine, we understand what the FFT seems to be doing, and we understand how the kappa vector is arranged. We understand the output. Okay? Now, this might still seem a little bit abstract. So let's do this. Let's turn signals into sounds. What is the command? Sound something. Sound Y. Sound Y. Yes. Okay, fine. When you play a pure note, well, you know what a pure note sounds like. Maybe not. So let's see. Do you know what 20 hertz and 20,000 hertz are?
Yeah, the limits of what is audible to us, the human ear.
Do you know, all of you? Humans can only hear sounds that are higher than 20 hertz in frequency and lower than 20,000 hertz. Below 20 hertz, we cannot hear things. Our ears are not sensitive enough. So that's called infrasonic. And higher than 20,000 hertz is called ultrasonic. That's the dog whistles. Okay, so anything below 20 we will not be able to hear. So let's see, let's make this 30. Okay, and then we need a lot more points to make sure we don't alias. And then, Yeah, I always have trouble playing with this part. I don't get the signal for long enough, or fine, let's do this. Okay, yeah, perfect. Let's see. So let's make our duration a bit longer, which means, let's see, length equals 5 seconds. I will multiply length here. Then I will also need to multiply length here. Did I mess something up? Wait. Oh, I should not do that. Okay. Wait. Okay. 31 should be fine. Fine, you get the idea. So see, we are going from 0 to 5, 10 pi, basically, 0 to 10 pi. And we have a signal with 20 hertz in there, 20 hertz. So there's 20 waves in every 2 pi. So there's 20 waves within the electrons. And the higher the frequency, the sharper it will sound. So 20 sounds like that. 30 will sound, okay, makes sense? 40 might not work, let's see. Maybe it will. Yeah, it works. Yeah, so, okay. It's a very common way of processing signals, using uh, uh, oral representation instead of a visual representation. Fine, let's do some stranger things. So, yeah, 2 we can barely hear. It just seems like a damn. So let's work with 20. Okay. What happens now if I do this? Let's visualize it first. Maybe it's easier. So sine 2x and sine 4x. I have added the two. What will the signal look like?
It will be one signal superimposed over other.
Yeah, it will basically look like one big sine wave with frequency 2, that's the longer wavelength, and the other one with frequency 4, that's the shorter one. So they will be superimposed. So we visualize this. Yeah, okay. So that's basically 2 different sine waves. Let's make it little more. Let's take 1 and let's take 10 over here. Okay. So you see there's, and let's go back to length 1. Okay, perfect. So there's one full sine wave. That's the sine 1x. And then there's the sine 10x. So there's 10 frequencies in there. And the FFT will basically break this up into the 2 different parts. Let's see if it does that. So all we need to do is compute the pi hat. 1001 to any. Let's see. I should be able to work with, let's say 31 points. Wait. Okay. And then what? Where do oh. Okay. All right. So y hat should have what? With the sine 10x and sine x, y hat should look like what?
since it is not normalized right now, it will be 31, 30 for,
It's normalized here.
oh yeah, then it would be 1
One for,
10x and another one for sin x.
does everybody agree?
Yeah.
Why do you agree?
Why do that's just what I think too.
Okay, so you think you'll get a non-zero f hat for kappa equal 10 and another non-zero f hat for kappa equal 1 because this is kappa equal 1, right? So yeah, that should be indeed the case. Let's see. So where is my y hat? Okay, I don't know what kappa vector looks like. So kappa vector 0, 1. Okay, so the second element should be non-zero. Yeah, it is non-zero. Okay, and the last element should be non-zero. Yeah, that's true, non-zero. Okay, then kappa number 10. Okay, that's the 11th element because it starts at 0. Okay, let's see. What is this? 9, 10, 11. Yeah, there's a non-zero term. Okay, and then minus 11 should be non-zero. Minus 11? No, minus 10. Yeah, so this one. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so that corresponds to minus 10 over here. Okay, and the easiest way of visualizing this is just doing a plot. Figure, plot, kappa vector, and absolute of what? Y hat.
Same limit.
Once more.
The y hat size and vector size won't be same, right?
Because 1 to 30 and kappa is 1 to 31. Oh, sorry. Yeah, so this actually starts as minus n over 2 minus 1. Yeah, that's correct. Yeah. Okay, so what is happening? Let's see what is happening. So we have, actually, let's do this. Perfect. So x-axis is kappa. And y-axis is y hat, absolute of y hat. Oh no, what did I do? Oh, yeah. Okay, so you see all the kappas are 0, well, all the y hats are 0 to machine precision, except for where we put the energy. We put the energy at kappa equal 1, which goes to minus 1 and 1, equally divided. And we put the energy at kappa equal 10, which again goes to plus 10 and minus 10, equally divided. Does this make sense?
Yeah.
So this is what signal processing, this is the basics of signal processing. Any signal you take can be decomposed into sines and cosines. Now, why is it 0.5? And why are there two terms, plus 10 and minus 10, plus 1 and minus 1? Okay, so, all right, just remember this is 0.5 for all of them. And the function we took was here, sine 10x and sine x. Okay, if we think about what we've been able to do, we've been able to reduce our information from this big plot containing 31 numbers into 2 numbers. You just need to give me f hat of kappa equal 1 and f hat of kappa equal 10. And tell me everything else is 0. Okay? With these two things, I can reconstruct the signal exactly with no error. Okay? So let's see. Yeah. So you tell me that f hat of kappa equal minus 1 or plus 1 is 0. No. Okay. One will be plus and the other will be minus. Let me just check. Okay, for kappa equal 1 is minus 0.5 I, and for f hat of minus 1 is plus 0.5 I. Okay, and f hat of 10 is also minus 0.5 I, and of minus 10 is plus 0.5 I. Okay, so I have these four numbers. What should I do with them? I want to recreate my signal.
Since we know that it will be, these are frequencies for sinusoids, we can simply put it in the formula for sinusoids.
Okay, yeah, that makes sense. So we said that our f of x, okay, so we have to talk about the inverse transform. So inverse Fourier transform. It just says that f of x is the integral from minus infinity to plus infinity f hat of kappa e to the plus ikx ek. Okay? And discretized, this will just look like, again, we don't have an f hat of kappa that's continuous. We don't have minus infinity to infinity. So the discretized equation will just look like f of x equals minus kappa over 2, n over 2. Kappa equals minus n over 2 to plus n over 2. And in here we'll go f hat of kappa e to the I kappa x delta kappa. Okay? There's just a plus minus difference between the forward transform and the inverse transform. And of course the limits are kappa versus x. Okay, and now this should make sense to you. Remember the kappa vector? It was perfect integers. So that's exactly what we're doing. We're taking kappa equal minus 5, minus 4, minus 3, going all the way to 0, and going to 1, 2, 3, 4, 5. That depends on my n, the number of grid points I take. And for each of these, I have a stored f hat vector, which I just gave to you. And e to the ikx delta k. Delta k is just 1 for us, because kappa vector. That's the way we implement it in math. What is e to the ikx?
I'm sorry. Can you just repeat what you said about delta k?
Delta k for us is 1, because remember kappa vector goes from 0 to 1 to 2 to 3. So the difference between the elements is 1.
Okay. So if we are not, if the Fourier series does not discretize on basis of 1, 2, 3, then we need a delta k when we discretize, write a discretized form, is it?
Yeah, because see that you always have to try to be as close to the integral as possible. And dk becomes delta k. Right? BFFT makes life easier for us by doing delta k directly. By the way, FFTW is what MATLAB uses. When I type FFT, MATLAB calls FFTW. Okay? Right, what is e to ikx? Remember, we're talking about sines and cosines.
Cosine of kx plus I sine kx.
Yeah, it's cosine of kx plus I sine kx. Okay? So, help me write out the summation f of x for our given data, right? Plus minus 1 and plus minus n, right? So, what will it be? Let's write out the symbol first. So, let's see. F hat of what?
Positive 1.
Let's see, plus 1 e to the, yeah, go on. We're just expanding the sum for the moment, right?
So it's just ix.
Ix.
Um, to the negative 1 of e to the negative ix plus I hat of 10, or f hat, sorry, 10 e to the 10 ix, yeah, plus f hat negative 10 e to the negative I 10x.
Okay, so we didn't do anything special. Fine. So let's see. Now let's plug in our values. Everything was no, not everything was. Factor 1 gives me 0.5 I. So this is minus 0.5 I times
Cosine of x plus I sin x.
cosine x plus I sin x. Yes. Next.
Positive 0.5 I.
Yeah, f hat of minus 1 was 0.5 I plus 0.5 I.
So cosine x minus I sin x. Minus 0.5 I. Cosine x plus I sin I. Or 10x, yeah. I sin 10x.
Go on.
Plus 0.5 I. Cosine 10x minus I sin 10x.
Yeah, just in case it's not clear, the cosine x minus I sin x comes from the e to the minus I. If the sign is negative, cosine doesn't care, so cosine remains as x. All right, simplify.
You can cancel the cosines. So negative 0.5. Oh, no,
Will be
sorry,
sin
positive
x.
0.5 sine x. Because I times I is negative 1. So 0.5 sine x.
Let's write it out for one case, just so it's clear. 0.5 times I sin x, right?
Mhm.
Plus 0.5 I
Times negative.
minus I sin x. Okay, and okay, next.
Cosines canceling in. So negative 0.5 I.
Now we can do this. I sin 10x plus I times minus I is plus 1, so we have 0.5 sin 10x. Right? What does this become?
Should the third term still be positive if you left the I? Sorry, you should just cancel that I
Yeah.
for the third
Yeah, I said I times minus I
The
is
term before
minus
that.
1. Oh, yeah.
Yeah, you can try.
Okay, so what do you get? Sin x plus sin 10x. Okay, just with 4 terms. Actually, just with 2 terms, you can recover the exact function. That's the beauty of Fourier transform. Yeah. Okay. Any questions at the moment? Yeah. Go ahead.
So, when we were talking about Nyquist frequency, and we need to know what all so suppose that if I don't know what frequencies a particular signal will possess a priori, how will I decide the grid size in?
Okay. So the question is, when I'm working with data, wait, you mean you're trying to acquire data or not?
I have the data, but I'm not sure what frequencies it does possess.
If I give you data points, let's say, okay, somebody else answered this for us. If I give you data points that have 500 points, xy coordinates, 500 xy coordinates, what can you tell me in terms of what are the frequencies that are in the data?
But at the first place, how will I acquire it? Because I don't know.
Yeah, okay, we'll come to that. But let's assume I give you 500 points. What do you know? What is the highest frequency that data should contain? It should not contain anything higher than
250.
250 hertz. Okay. This is me assuming that you have taken care of this.
Yeah.
you have given me 500 points because you know the data does not contain anything higher than 250. If it does, it will be aliased and your analysis will suffer. Okay? Now, where do I get these 500 data points from in the first place? Let's say I have a mic and I'm recording somebody singing or playing the drums. And I say the drum has a low frequency range. It's all bass, so nothing above 250 is important, the sound of the drums. So then I can say, yeah, okay, I can record this with 500 samples, 500 ones. I'm not limited to that, I can use 50,000. The amount of data I have to give you, I have to keep, I have to store is 10 times larger. Okay. So that's where this is very handy. If you say that, no, there's no frequency higher than 250 that's important, you're just wasting gigabytes. There's no point in saving more data. Does this make sense? This is exactly what the sampling rate, etc. When you play music, it's the higher frequency, higher sample rate is more data points, the file size is bigger, but it's more accurate because it contains more frequencies. What should be the highest frequency that the MP3 should be sampled at?
20 kilohertz.
What's more?
20 kilohertz.
True or false? Why 20 kilohertz?
Because people cannot hear beyond that. So
Yeah, we cannot hear anything higher than 20 kilohertz, 20,000 hertz. But you have forgotten the Nyquist frequency.
yeah, it would be 40.
It should be sampled at 40,000 hertz at least, right? Because of the Nyquist frequency. To represent this largest frequency, you need at least 40,000 watts. So that's why you might see most MP3 files have a 44 kilohertz sampling rate, which is usually sufficient. I mean, we cannot hear anything higher than that. Some people who are audio aficionados, they might say, oh no, we need it. But you cannot hear it, so you don't need it. Okay, and Fourier transforms are also used for, again, for MP3 compression. They're also used for JPEG compression. So you have a visual picture, and it contains many small frequencies in space. Okay, you don't need all of that to get a rough picture of what you're looking at. If it's a cat picture with a million points in a small picture, fine, it looks nice. But if I reduce that to 100,000 points using Fourier transform, it might still look reasonable. You might not be able to tell the difference. So a lot of data compression uses Fourier transforms. Be it sound, be it visual signals. And again, it's a very big advantage. You can store just two numbers and reproduce a whole signal as we did on paper. So this is very, very useful in many fields. Okay, we did not get to how to use this with PDEs, but I can tell you next time. So yeah, let's stop there and we can continue next time. So I will post the last project and it will be 30 points and it will be solving the Navier-Stokes equation. You will have a full month to do it. It will be due at the end of the term. Also, there will be an extra credit project. It's 10 extra points if you do it, and if you get the full points. And I will write up both of them and put them up sometime this week. Okay. All right. Yeah. See you next week.
Does the extra credit project also do at the end of the term?
Yes. Yeah.